Hello, everyone. And here we are on day 3, I guess. Let's see how many are here. 45 are here. And we'll see if any more come in. All right, so let's see. Anybody got any news? You hear anything? Anybody feel the earthquake?
There's an earthquake?
Yeah, there was an earthquake today up in north of Los Angeles. 5.4, something like that.
Oh, was I mean, was it okay? I mean, I didn't feel it at all. What time?
Yeah, I didn't feel it either. It was sometime in the middle of the day. Yeah, it was just that was exciting. I'm going over to campus after class. The guy said maybe fix my key, so that pool looks so cool.
They're going to let you in even though they have all the signs outside. No one's allowed in except for
there's a
faculty. And
no, what you do is you just tell the dean. Apparently Mariana went over there a few weeks ago without a face mask and just kind of hung out for hours and hours. And then all the deans got a email saying you have to give them permission or something like that. So anyways, we just text the dean and then we go over. I make sure that I wear my my face mask though.
Yeah.
Okay, I'm going to share the screen here. 1, 2, here we go. All right. Now, where is OneNote? All right. Get into this right now. All right. So before we do anything new, any of you guys have any integrals you want to see done that you may have had trouble with?
The sum yesterday you assigned as a homework, the integral of sine power 6x and cos 4x, it was almost impossible to do. Could you?
Sine 6x cosine 4x? Yeah. Oh yeah, that's a nut buster right there. That's going to be terrible, but it's good for you guys to practice it. I don't need to practice anymore. But you would turn this into 1/2 minus 1/2 the cosine of 2x cubed, and then 1/2 plus 1/2 the cosine of 2x squared. Like that. And what I'm going to do is I'm going to write it like this. I'll say it's 1/2 minus 1/2 the cosine of 2x squared. And then one of these guys I'm going to multiply with that one to give 1/4 minus 1/4. That's going to bug me. Minus 1/4 cosine squared of 2x. And then you'd have to FOIL this guy out, distribute it all. You're going to have a cosine to the 4th and But anyways, that was good that you're doing that problem. I like that. Okay.
Yeah,
Any others?
Just went out pretty long, so I thought I got lost. I just wanted to clarify.
Yeah, it's one that's going to take a very long time.
I have a question.
Yep.
So at the beginning, you changed it from like sine to the power 6x and then cosine 4 to the power 4x and so on, and you change it to 1/2 minus 1/2. How does that go?
So the identities are this: cosine squared x is 1/2 plus 1/2 the cosine of 2x. Sine squared x is 1/2 minus 1/2 the cosine of 2x.
Oh, okay.
And notice that when you add those lines together, you get sine squared plus cosine squared is 1. All right.
Okay, I see it now.
Okay, so any other integrals? Gave you fits? Anybody want to do this one? The integral of x over 1 plus x to the 4th dx. Let's see, probably a u substitution. All right, so what do you want to let u equal?
x4.
X to the 4th. So du would be 4x cubed dx. So somehow we need to get, there's a 4x squared times the x dx. Okay, so if we could somehow write 4x squared in terms of u, that would be awesome. The problem is, if we say that x to the 4th is equal to u, x squared is going to equal plus or minus the square root of u. And that's kind of a bad place because now we got to choose. Okay. All right. But you've got some skin in the game now. Okay. You made an attempt and there it goes. Sometimes it helps to let u be the entire denominator. But if we try that, we would run into this exact same problem again. Okay. Back to the drawing board here. Now, don't any of you guys from my last semester class remember how this goes? You let u equal
Tan
u equal x squared. So that means that x to the 4th is u squared. And du is 2x dx. So do a Plackmeyer trick. This is what my high school calculus teacher would have done. He would have inserted it like that, and then he'd say, okay, now it's going to be 1/2 du divided by 1 plus u squared. Okay, what's the antiderivative of 1 over 1 plus u squared? Nobody today? Tan inverse of u plus constant c. Start with x, end with x, so it's going to be 1/2 the tan inverse of x squared. Okay, so for you guys that haven't been in one of my classes before, what I would have, this is like something I might put on an exam, but what I would do is I would put 2x in the top, just so I wouldn't have to deal with that 1/2. Okay, but anyways. Okay, so speaking of Plackmeyer, my high school calculus teacher, we were doing calculus with, the approach was not the
A little
approach.
bit, just a little bit.
What?
Just go up a little bit. Not that much. You can just this last section. I just need the last one. That's perfect. Thank you.
Okay.
You can go down now.
So one day in class, Plackmeyer comes in and he's going to show us how to do this integral. Okay, now one of you tell me, what is this integral? Somebody tell me.
sine inverse of x.
Yep, sine inverse of x. Okay. You remember how we got that? Just let me refresh your memory here real quick. What we did is we said, okay, if y is the sine inverse of x, then x is equal to the sine of y. So if we take the derivative of both sides implicitly, 1 equals the cosine of y times y prime. So y prime will be 1 over cosine of y. Cosine of y is the square root of 1 minus the sine squared of y, which is equal to 1 over the square root of 1 minus x squared. So the derivative of sine inverse is that, so therefore the antiderivative is that. Okay, now, I wasn't doing early transcendentals in high school. Transcendental functions are the inverse trig functions, the logarithms, the exponentials. All of us here at Coast, you know, basically on my recommendation 21 years ago, I said, let's go to early transcendentals because there was just way too much material up there in 185. So when you don't have the early transcendentals, what you can do is some kind of a substitution. So Plackmeyer, one day, he says, all right, well, let's think about this. For what values of x are we allowed to use? Well, we can use -1 less than x less than 1. And we can't use the endpoints because of division by 0. Okay? All right, so then he challenged us. He said, can you think of a function that takes its values between -1 and 1? And it was probably Eric Prosser who said, you know, yeah, it's the sine function, okay? So here what we're going to do is a different type of a substitution, okay? We're not going to let u equal some function of x. We're going to let x be some function of a new parameter, which we'll call theta, okay? And x is going to be the sine of theta. Now, notice that the sine of theta runs through all of these values, just like x is going to be doing, okay? And then when we go and calculate dx, we're going to get a cosine of theta d theta, okay? So you plug all of this stuff in, and we were just kind of watching him do his stuff, you know, like so, divided by the square root of 1 minus x squared, which is sine squared theta, which is the integral of cosine of theta d theta, divided by the square root of cosine squared theta. Okay, now the next step. You're going to have to be careful with this. You're going to run into occasions where the square root of something squared is not just the thing. But since we're only doing symbolic manipulation, we can do that. So then we just end up with the integral of d theta, which is, of course, theta plus a constant c. And theta, well, x was the sine of theta. So theta is the sine inverse of x plus constant c. So this is how we did it in high school, okay? Because we didn't do the early transcendentals. And I remember it was very late in the semester. I already knew where I was going to college. Major I wanted was impacted. There, the earthquake, 5.8 up in Lone Pine. So I guess that's really far away from Los Angeles. Anyways, I started paying more attention in class because I was going to be a math major, not by my first choice. And anyway, so I started paying attention, and I remember this day quite well. Okay. All right. So what this leads to then is this new kind of idea. Okay. Section 7.3, trig substitution. Substitution. That's got to be wrong. Substitute. Say that word over and over again. It'll sound weird. Okay, so when we are integrating functions like f of x dx, and maybe f of x, I think my dogs are going to start screaming in a second. Sounds like a delivery truck just pulled up. If the function is or involves stuff like this, the square root of a squared minus x squared, the square root of x squared minus a squared, x squared plus a squared. Basically, anything that looks like it comes from some kind of a trig identity. Okay, here's what I mean by that. Remember that sine squared theta is 1 minus cosine squared theta. Okay, so if this was like an x, you know, you could also, in the above problem, you could have let theta be, you could have let x be the cosine of theta. Okay, I'll show you how that goes in a second. Okay, and we want to take advantage of the other one, which is the tan squared x plus 1 equals secant squared x. Okay. All right, so why don't we just get right into it? All right, so let's try one of these guys. So for example, why does it always do that? For example, let's go with the integral of the square root of x squared plus 1 dx. Okay, so anytime you have something squared plus something, and it's both pluses, you might want to start thinking about the tangent one, okay? There is no restriction on x in the integrand. You see this? Because it's just being squared. It's not in the denominator or anything. It's always going to end up positive, okay? So maybe if we were to let x be the tangent of theta, okay, then dx would be the derivative of that, which is secant squared theta, d theta. Okay, so now we plug in and we get the integral of the square root of tan squared theta plus 1 dx secant squared theta d theta, which is equal to the integral of the square root of secant squared theta, then another secant squared theta d theta. Okay, now since there's no bounds here, we're just doing symbolic manipulation. And so with the symbolic manipulation stuff, the square root of secant squared is just going to be secant. So what we end up with is this integral that I told you guys about yesterday, okay? This thing is going to show up a lot. So we probably want to have it memorized. Okay, now I have it memorized. 1/2 of secant x tan x plus the natural log of secant x plus tan x plus constant c. Okay.
Professor, excuse me, do you mind if you scroll up a little bit?
Scroll up.
Yeah, I will take a screenshot of the example. Little bit down. That's it. Thank you. Wait. Oh. Thank you. That's it.
Okay, hold on 1 second.
Professor.
Hold on, somebody's at my door. Wait.
Okay.
1 second.
I don't know what that line is next to secant x and tan x.
I think it's just a parenthesis.
Is it? Okay.
Yeah, because we're just multiplying them to eliminate them.
Oh, so it's like natural log times like secant x plus tan x, right?
Exactly.
Okay.
Okay, that was just Amazon driver. All right, so this is secant. Wait. This is all theta. Okay, secant. Here, let me write it again. Oop. Okay, so it's 1/2 of secant theta times the tangent of theta plus the natural log of secant theta plus tangent of theta plus constant c. Okay, now remember, this was in x, right? And so we're somehow going to have to undo this substitution that x is the tangent of theta. Okay, so for the handful of you guys that were with me back in pre-calc, when we got to the trig stuff, I said, this is going to show up in a couple semesters. What you do is you draw a triangle that represents the substitution. Okay, so if this is theta, the tangent of this angle, you could write as x over 1. Now we want to complete the triangle like so. Okay, and what is the tangent of theta? Well, that's x, but what about the secant of theta? Well, according to our triangle, the cosine of theta would be 1 over that, so therefore the secant of theta would be that over that. Okay, so our integral, which was the integral of the square root of x squared plus 1, dx, is equal to 1/2 of the secant of theta, x squared plus 1, times the tangent of theta, maybe I should have put the x in front, plus the natural log of the secant of theta, plus the tangent of theta. Okay, so kind of unexpected, I guess, in a way. So this kind of substitution is a different style. I'm gonna have to do something here. I'm gonna have to, somebody came in the room. And I gotta, I'm hearing my echo. Okay. Boom, 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 boom. Share my screen. Great. Okay. There we go. All right, turn this thing around again. Okay, so any questions on this guy?
So for the secant cube theta, you just split it, then you do it individually, right? And then you get to that answer.
The secant cubed integral is an integral we do by parts, and we did that yesterday. Remember
Oh,
that?
yeah, right.
And I said, this thing is going to keep showing up, so you might as well just write it down somewhere because it's always rearing its ugly head.
Professor, after the absolute value ends, would you end the parentheses as well? Because that's what
Yeah.
Cool. Just wanted to double check.
That's me trying to draw parentheses.
Eh,
And that looks like some serious Parkinson's going on there.
kind of like brackets almost.
Yeah, maybe. Okay, so now I want you to make sure we all recognize the difference. the first type of substitution that we were doing was u is some function of x. You know, like, for example, in the integral 2x square root of x squared plus 1 dx, u is this function of x squared plus 1, okay? Now we have a new type of substitution. X is going to be some function of theta. And it's generally either going to be some kind of a number in front of some theta, or it's going to be b times the tangent of some theta, okay? You generally always use the x equals sine or the x equals the tangent, okay? All right, now I'm just going to do a bunch of these problems, and maybe some of it will stick, you know? All right, so I'll try to hit all the kinds of flavors that we've got here. The integral of x cubed times the square root of 9 minus x squared dx. Okay, so is this going to be a sine and cosine integral, or do you think a tan and a secant?
It's gonna be a 10
Why do you say the tangent?
because of the cube in front of the root.
Well, what does the whole thing is this. This is what's indicating it, okay? So just remember, anytime you're going to be doing this, this is going to be some kind of a sine and cosine type of a deal, okay? Now, I'm going to do this like a couple different ways. Like this one is easy enough to where I can say, all right, let's let x be 3 times the sine of theta. Why do you ask? Because 9 minus x squared is going to be 9 minus 9 sine squared theta, which is going to be 9 times 1 minus sine squared theta, which is going to be 9 cosine squareds of theta. Dx, this is the thing that sometimes we all do this from time to time, forget to throw that piece in, okay? So now our integral is going to be x cubed, so that's going to be 27 sine cubed theta times the square root of 9 minus x squared, which is 9 which is 9 times the cosine nine cosine squareds of theta d theta. And we're just doing symbolic manipulation. So a 3 is going to come out. 3 times 27 is going to be an 81. Integral sine cubed theta cosine of theta d theta. And I think we know what to do here, right? So now we do another u substitution. U is the sine of theta. So du is the cosine of theta. D theta. Okay, and so we still have this 81, and then we're integrating u cubed du. And so that's going to be 81 u to the 4th over 4 plus constant c. 81 over 4. The u was sine of theta plus a constant c. And our original substitution was the sine, well, the original substitution was x equals 3 sine theta. So that means that the sine of theta is x over 3. Again, you draw a triangle representing the substitution, x over 3. Now complete the triangle, 9 minus x squared. And notice that that is a part of the integrand. That's a good indication that you're doing it right. If you don't get that, it's a pretty solid indication that you're doing it wrong. Okay, so we didn't really need to complete the triangle here because all we have is the sine to the 4th theta. So that's going to be 81 over 4. Then it's going to be x to the 4 over 3 to the 4th, which is x to the 4 over 4. That can't be right. What did I do wrong here?
In the part, the example, like you had like the ds equal to 3 cos theta, theta, and then when you replace these, I think you missed the 3 cos theta.
Good. You were paying attention. Didn't I just say this? Sometimes, you know, we you know, forget to do this. All right, so everybody wake up. All right, but we're still good to here. So let's do this. Let's go with all this stuff. And remember to put in, well, this was one of those deals where I did it on purpose, but occasionally I will mess it up. Okay, so our x is 3 sine theta. Okay, so our integral, my pencil again. My integral now becomes x cubed, which is 27 sine cubed of theta, times the square root of 9 cosine theta, and now the 3 cosine of theta d theta. All right. And this is going to be, what's 81 times 3? 243? 243 integral, and now I've got sine cubed theta cosine theta squared d theta. Okay, so we know what to do now. 243 is out in the front, and I'm going to write it as 1 minus cosine squared theta cosine squared theta sine theta d theta. So what I did is I broke one of these off and I turned the resulting sine squared into this. Okay. Now if you were to let u be the cosine of theta, the du is going to be negative sine of theta d theta. Okay. So I got a 243 here, and then it's going to be 1 minus u squared negative du, which I will get rid of that negative sign right now by writing it as u squared minus 1 u squared du. And this is 243 integral of u to the 4th minus u squared du. Okay, so it's going to be 243.
How do you write use 1 minus u squared as u squared minus 1?
Remember this negative sign?
Oh yeah, got it. Okay.
So I just kicked it because if I go any further, I'll lose it. And that won't be intentional. That'll be me losing it. Okay, so now it's going to be u to the 5th over 5. U is cosine. So it's cosine to the 5x over 5 minus cosine cubed x over 3. I mean, theta plus a constant c. Okay, now our substitution was that x was equal to 3 sine theta. Okay, so x is equal to 3 times the sine of theta. So that means that the sine of theta is this x over 3. You draw the triangle to represent the substitution, x over 3. Complete the triangle, that's theta, 9 minus x squared. And the cosine of theta in this picture, this is 243 times 1/5. The cosine of theta is radical 9 minus x squared over 3 to the 5th power minus 1/3 times the square root. Wait a minute. The 5th power only applies, doesn't apply to the denominator here. It only applies to the numerator. So it's that to the 5th power. And then this is going to be let's see, that, and then it's going to be the square root. Why do I keep doing that? It's going to be 9 minus x squared cubed over, well, I already got the over 3. This, what am I doing? This isn't supposed to be here. It's gone. And then, like Brian said, close it off. Okay. What do you think about them apples, huh?
So wait, it's gonna be I2. Okay.
Yeah, these trig substitution problems are just big old puzzles that you try
It's
to.
it's 1/3 to the. Is that 3 or 5 power?
This is a 5, and this is a 3.
Okay.
Because it was a 3 up there.
Isn't it square root of 9 minus x squared over 3, the whole 5th power?
Was it? Did I have it right the first time?
Yeah, because that's the cos formula, right? The adjacent over the hypotenuse.
So the cosine, yeah, it was. So we did need the 3. And we did need the 3 in the other one. So bring this down. So what happens? I'm looking too close. This was at the board. Okay, well, anyways, then plus constant C. All right, so let's do some other types that can show up here. All right, so let's try this guy. How about, let's see, this is always an interesting one. The square root of 1 plus x squared over x dx. Okay, now if this problem was flipped upside down, it would be quite easy, don't you think?
It would be a U substitution.
Right. Sadly, it isn't. Okay. All right. So anytime you see 1 plus something squared or a squared plus x squared, or anytime it's all positive like that, you want to be thinking in terms of tangents and secants. Okay, so our substitution, since tan squared plus 1 is secant squared, we should let tangent theta be x. Dx is then going to be secant squared theta, d theta. Okay, and we can plug everything in here. That's going to be the square root of 1 plus tan squared theta. Then the dx is the secant squared theta, d theta. And down here, I have the tangent of theta. 1 plus tan squared is secant squared, squared is secant, squared is secant. So we end up with secant cubed theta divided by the tangent of theta d theta. Now that would have been awesome if the secant cubed was instead secant squared, don't you think?
Mhm.
Yeah, that would have been easy. Okay, but sadly it isn't. Okay, so let's see here. Maybe we sine and cosine the thing and it'll help. 1 over cosine cubed x is, theta. Okay. And then the tangent of theta is the sine of theta divided by the cosine of theta, d theta. I don't know if this is the way to go. I'm just trying it. Okay, integral. It's going to be 1 over, what's going to be d theta over, then it's going to be cosine squared theta sine theta, which we can write as secant squared theta cosecant theta d theta. Okay. All right.
Hey,
Now,
Professor, Bobby, why can't you just keep it d theta over cosine squared theta sine theta? Why does it always need to just have the stuff in the numerator?
it doesn't. It's just that, okay, so what I'm looking at, you're talking about why
Yeah,
did
why do we choose to keep going, and why do we choose sometimes just to end? That's the thing I think I've been the most confused with integrals a lot of times.
Okay, well, at this point, let me tell you what's going on in my head. And okay, so I get it to here and I see this, all right? Now, there is no U substitution that's going to work here, but if I can write it as a product, I can use integration by parts.
Okay.
And so this is what I've done. I've changed this quotient into a product. Okay, and so now I can use parts. I think U equals cosecant of theta dV equals secant squared theta. Du is going to be negative. Cotangent. These dogs are about the size of maybe 2 40-ounce thermal flasks. But they sure talk a good game or bark a good game.
They're not Yorkies, right? You said?
Yeah, they're Yorkie, Morkie, something.
Oh, I had Yorkies when I was a kid. Yeah, they like the bark.
Yeah, and
Anything to do.
tangent of theta. Okay. All right, so U is cosecant. Oakley, quiet. That ain't listen to me. It's like my kids. Okay, so if u is cosecant, I'm gonna walk down the house right now. Okay, so this is me doing integration by parts. Now, before we go any further, let's look at this. Okay, we start off with this guy right here, and we go directly to trig substitution. Okay, the trig substitution is now requiring us to do integration by parts. Okay, but as long as I don't run into any roadblocks, Brian, I will keep going. And I'm seeing something right now. UV, so that's going to be cosecant of theta, tangent of theta, minus the integral of negative cosecant theta, cotangent theta, tangent theta, d theta, which is equal to cosecant theta, tangent of theta, plus the integral of cosecant of theta, d theta, because tangent times cotangent is 1. Okay, so now for this guy, if we multiply the top and bottom by cosecant theta plus cotangent of theta, this is that problem I wanted you to do last night. Cosecant of theta plus cotangent of theta, d theta. Then I'll let u equal the bottom. Du is going to be negative the top, d theta. Okay, so it's cosecant of theta. I don't know why I'm not changing that to cosine. I'm going to change the cosine in the next step. Okay, and then it's going to be then minus the natural log, because u is the whole bottom. So it's cosecant of theta plus cotangent of theta plus constant c. Okay, now way back where our substitution when we started was x equals the tangent of theta. Okay, so the tangent of theta is equal to x. We draw the triangle. Here's theta, x, 1. Now we complete the triangle, 1 plus x squared. And we need to identify what the cosecant is. Okay, so the cosecant is 1 over sine. So cosecant is going to be 1 plus x squared over x times the tangent of theta, which is x, minus the natural log of the cosecant of theta, which is that same thing, plus the cotangent of theta,
You just
Where-
wrote.
where was it?
I think
Oh,
you-
the cotangent of theta is 1 over x. Okay, plus constant c. And then if I had done this a long time ago, we would have just been left with that.
Oh, so we just crossed them out. Wow.
Yeah. But go up here. Cosecant times tangent is cosine. I mean, is 1 over cosine. And so cosine is 1 over the 1 plus x squared. So 1 over the cosine would be the thing we got. Okay. And plus the 1 over x plus the c. Okay, so there's a lot going on here. Now it's, to tell you the truth, the last time I did Math 185 in the summer, several years ago, Professor Guerra's kid was in Math 185, and he's now a grad student at Berkeley in physics. So that's quite some time ago. But what I do remember is the timing, you know. When I say during a normal semester, you really need to integrate. In the summer, it's almost like you have to just wake up and start integrating, you know. It's even, you know, even with you guys being able to look stuff up and this and that and the other, you still need to learn how to do this. And hopefully, you know, you've got enough time to spend over this next 7.5 weeks in order to do some of this stuff. All right, let's try another one out of the book.
So wait, the natural log actually gets canceled out in this problem, right? With the solution, for the solution.
Yeah. The natural log? No, it's sitting right there.
Oh, we don't cancel it out, right?
Nope.
Okay.
It's there. It stays there. Okay, so here's a new twist. So we're gonna go the integral of dx over the square root of x squared minus 6x plus 13. Okay, so what's new here is this negative 6x piece that I've got. Okay, somehow I gonna have to play with that.
Don't we just take out the square at the bottom by doing the conjugate?
Well, what would the conjugate be?
Wouldn't it be x squared plus 6 minus 13?
Okay, so maybe you would x squared plus 6x minus 13.
Yeah.
Try it and see what happens. What you'll find is that it doesn't quite get you what you think it's going to get.
Oh, okay, I see.
Yeah. Even with the cubics,
Mm-hmm.
there's a conjugate for cubics,
but
it doesn't look the way you think it looks. Maybe one of these days I'll come across a problem that we use it. Okay, so what we're going to do with this guy is we're going to try to get rid of the negative 6x. Okay. Now the way we do that is by completing the square. So this is x squared minus 6x and then plus 9 plus 4. Okay. And now the question has been answered. Do I need to know how to complete a square now that we know the quadratic formula? Well, yes, because sometimes you're not just after the one number that's the answer. Sometimes you're after more. Okay, so this is going to be dx divided by the square root of x minus 3 squared plus 4. Okay, now we're just going to let t be x minus 3. So dt is the same as dx. Okay, so now I have the integral of dt divided by the square root of t squared plus 4. Okay, I'm going to lock the dogs up. Time out. Come on, dogs. Okay, come on. This way.
Hey, Jaeger is not going to be able to record class tomorrow, so if one of you guys can, you drop it into the Discord, that'd be cool. If no one's willing to, I can try to figure it out, but I'm not going to make any promises.
All right, not lock them in the bedroom. Okay, so now we're in position for one of our trig substitution things, okay? So it's pluses, so we think of tangents and theta, tangents and secants. let me show you the way I do these things when they get kind of complicated. What I want to have happen is that t squared plus 4 is going to be 4 tan squared theta plus 4. Okay. So in order to get that, I back into it. I need t to be the tangent of theta. Okay, now after this problem, I'll do a more complicated one and you'll see how that kind of helps. Okay, so this is our substitution that we're gonna, t is gonna have to be 2 times the tangent of theta. Hold on, let me erase that. T is gonna have to be 2 times the tangent of theta. Okay. The dt in this case would be 2 times secant squared of theta, d theta. And now we're going to plug it all in. So in the numerator, we're going to get a 2 secant squared theta, d theta. And in the denominator, we're going to get the square root of 4 times tan squared theta plus 1, which is going to equal the integral of the secant squared of theta divided by, notice the 2 and the 4, the numbers cancel. Okay, secant of theta, tan squared plus 1 is secant squared, which leads us to the integral of secant of theta. Anybody remember that from yesterday? It's the natural log of
Log
secant.
mod secant x plus tan theta plus c.
Yep. Okay, now we got to undo the substitutions. All right. Okay, so what we had was that the tangent t was equal to 2 tangent theta. So that means that the tangent of theta is going to be t divided by 2. Okay. So now we draw a triangle, t over 2, complete the picture, t squared plus 4. Recognize that, okay, that piece is in the triangle, so we're good indication we're going in the right direction. Okay, so the secant of theta our integral is going to be the natural log of secant, which is going to be square root of t squared plus 4 over 2 plus the tangent of theta, which is t over 2 plus a constant c. And now remember that t was equal to x minus 3. Okay. And so our integral ends up equaling the natural log of the square root of x minus 3 squared plus 4 all over 2 plus x minus 3 over 2 plus constant c. Okay. Any questions about that, fella?
So will there be numbers usually which we can complete the square easily, like 13 or something like that?
If it's on my test, it's going to be easy. But if I just put some random one on here, it maybe not so much. Like, let me see here. Okay, this one might kill us. Okay, so it's the integral of dx divided by 9x squared plus 6x minus 8. Okay, so To complete a square, technically you would factor the 9 out and do it with the thing, but are we seeing anything here? Like if I go 3x, 3x, and then if we say plus 1, that's going to be 9x squared plus 6x plus 1. Okay, so this is going to equal the dx. Is that under a square root? Yeah, it's all under a square root on top of everything else. The dx divided by the square root of 9x squared plus 6x plus 1 minus 9. Okay. You get really good at algebra by doing integrals. Okay, so by design, this was equal to the integral of dx, and then it was the square root. Now that's going to be 3x plus 1 squared minus 9. Okay, so I'm going to let t be this 3x minus 1. Okay, then dt is equal to 3 dx. Okay, so if I put a 1/3 out here, 3 dx, that is going to give me the dt in the numerator. The denominator is the square root of t squared minus 9. Okay. All right, now we're going to use our trig substitution. Okay, so when it's the variable squared minus the number, you just need to know to do this. Now, if one of you asks me, I'm going to pretend you asked me, how do you know to do that, Bobby? It's actually not going to be that.
How do you know how to do it?
The reason I know how to do it, I know that that's the thing to do, is because of the amount of integrals that I have done. Now, you don't have to do as many as me, okay? But you do need to do a lot of them. And pretty soon you start kind of seeing in the dark, you kind of seeing what you're going to do. This substitution, t is going to be 3 times the secant of theta. So dt is going to be 3 secant theta tan theta d theta. Okay, so if I plug all that in, it's going to be a 1/3 3 secant of theta tangent of theta divided by the square root of 9 secant squared theta minus 1, which is going to be 1/3 d theta, the secant of theta times the tangent of theta divided by, I already took care of the 9. So tan squared plus 1 is secant squared. So secant squared minus 1 is tan squared theta. Okay. And so now we're just left with this integral that we just had a similar problem with. 1/3 the log of secant of theta plus tangent of theta plus c. Okay, now the secant of theta was t over 3. So the secant of theta would be t over 3. Complete the picture. This is going to be the square root of 9. Oops. This squared plus this squared gives us the hypotenuse squared, okay? And again, here's that thing. Okay, so our integral then is going to be 1/3 natural log of secant of theta, which is t, the pathetic looking t. I wonder if there's a way to make this Apple Pencil less sensitive. Maybe use a lower battery, like let it almost die. Okay, secant of theta, which was t divided by 3, plus the tangent of theta, which was the square root of t squared minus 9 over 3, plus constant c. And t was 3x minus 1. 3x minus 1 over 3 plus the square root of 3x minus 1 squared minus 9 over 3 plus a constant c. All right. Any questions on that guy? This radical actually extends out.
I missed it somehow.
All these ones that I'm doing, you should, after we're done, redo them. And maybe I'll peek over every now and then to see if you're getting it right. Okay, so that's a complete the square guy. All right, so, you know, that kind of stuff is out there for us. All right, let's see if we can do another one here. Let's see. Okay, how about this? Okay, so for example, let's try the integral of dx divided by x times the square root of 5 minus x squared. Okay, so this is going to be sines and cosines. Remember, what I want in my substitution is to have 5 minus x squared equal to 5 minus 5 sine squared theta. Okay, so what we need for that is x to be the square root of 5 times the sine of theta.
And this is using the identity, right? To complete.
Yeah, so I'm trying to use the 1 minus sine squared as cosine squared, because this is going to be 5 1 minus sine squared, which is going to be 5 times cosine squared.
Okay.
All right, so if you're looking at a mess, you know, you just write down what you want and then back into what you need. The next one I do will be a little harder, okay?
Okay.
So our dx now is going to be radical 5 cosine theta d theta. Okay, so our integral now is dx, which is square root of 5, and then it's sine theta, cosine theta, shoot. Cosine theta d theta. Downstairs, x is radical 5 sine theta. And then this is going to be 5 minus 5 5 minus 5 sine squared theta. And let's see, clean it up a little bit here. I'm going to get 1 over radical 5. That's going to come from this guy. These guys cancel. And it's the integral of cosine of theta d theta divided by the sine of theta. And then this is going to be the square root of cosine squared, which is just cosine of theta, which is 1 over radical 5, the integral d theta over sine theta, which we just got done talking about, how to integrate the cosecant of theta d theta. One of the things that makes this stuff so challenging is that it just keeps coming at you. I mean, you know, one thing after another. And so I can see how this can be overwhelming. Hopefully you guys all took a light summer load. Okay, so do we remember what the answer was to that? It was 1 over radical 5 negative natural log of cosecant, cosecant of theta plus cotangent of theta. Okay. And now our substitution. The sine of theta, that was x over square root of 5. So draw a triangle for this. X over radical 5. Okay, now complete the triangle. This is going to be square root of 5 minus x squared. That squared plus that squared is that. And notice that's the piece that we were anticipating. So negative 1 over radical 5 natural log of the cosecant of theta. Okay, so that's going to be radical 5 over x plus the cotangent of theta, which is going to be the square root of 5 minus x squared over x plus a constant c. And every now and again, take the derivative of what you got just to make sure you got it right. And also it's going to help you practice taking derivatives as well. Okay. Any questions on that guy?
I was a little bit confused why it was negative 1 over 5 radical 5 instead of
it comes from this.
Oh, because we got, okay, I see, because negative.
So we're going to multiply the top and bottom by cosecant theta plus cotangent theta. And then if u is the bottom here, then du is going to be negative the top, because the derivative of all the cos are negative.
Okay.
Okay. And there we go. Oops.
That filled in. Now my brain feels better.
Okay. Okay, now here's the sad news about this problem. If you were to look this up in the textbook as what's the answer, I took it right out of the book. What number is it? It's number X. Well, where the hell did I find it? Where's that 5? Jeez. There it is. Ah, shit, it's number 14. Okay, but this answer probably would not be what's reported in the book. And it all has to do with the antiderivative, this thing. Okay. If you move the negative inside, and now it's going to be 1 over those things. Okay. If you turn them, if you do a little manipulation and you get what's in the table of integrals. Okay. So maybe for homework tonight, redo this one, try to make sure you get to where I got. Hopefully I didn't make any mistakes. I don't think I did anyway. And then look up what the integral is in the textbook, like in the tables. I'll just look it up right now. Cosecant of theta d theta. Is it in the front or the back? Remember, I was just looking at it. It's in the front. Table of integrals. Oh, shoot, it must be in the back. Okay, so the cosecant integral. Where the hell is it? Cosecant. There it is. Okay, natural log of cosecant minus okay, now do you see the difference?
Yeah.
The plus, okay, so for that reason, when he plugs this stuff in, it's going to look different, right? Okay, so this is all stuff that I think you should maybe try to wrap your head around. Instead of here, listen to me go over and over and over. Like do what
It just looks like towards the end, he didn't do what you did, which is cancel out the negative. Instead of he moved the negative inside the
thing. Yeah.
Uh-huh.
But I mean, like I said, and this is something I think it would be worth your time to, get into and start looking at it. All right, well, let me get back to some more of these guys. Okay, so where's my set of exercises? Trig substitution. Okay, here we go. All right. Let's do the integral of the square root of 3x squared plus 5 dx. Okay, this is going to be some kind of a tangent and secant problem. Okay, so when I have this, when neither one of these numbers are 1, I usually will factor the thing in front of the x squared out. Okay, so if I do that, it's going to be the square root of 3 times x squared plus 5/3 dx. which is now going to be radical 3 integral of the square root of x squared plus 5 over 3 dx. Okay, now here's what we want. We want x squared plus 5 over 3 to be 5 over 3 tan squared theta plus 5 over 3, which would be 5 over 3 tan squared theta plus 1, which is going to be 5 over 3 secant squared theta. Now, we were going to have to do that calculation anyway, so why don't let's do it now. Okay, so the substitution that we need to make all of this happen, we're going to let x be the square root of 5 divided by the square root of 3 times the tangent of theta. Dx is going to be a mess. Square root of 5 over the square root of 3 secant squared theta. Okay, now, if you've been playing along here, you got to know what's coming. That secant cubed integral is coming again, okay? So it's equal to radical 3 square root of 3. Now I'm going to integrate the square root of x squared plus 5 over 3, which is going to be 5 over 3 secant squareds of theta times radical 5 over radical 3 secant squared theta d theta. Okay, so it's going to be 5 radical 3 over 3, because I got square root of 3 times square root of 3, square root of 5, square root of 5. Okay, and then integral of secant cubed theta d theta. So that's going to be 5 radical 3 over 3 times 1/2. So maybe I'll put the 2 down here. Secant of theta tangent of theta plus the natural log of secant of theta plus tangent of theta. Okay. And the tangent of theta.
Hey, Bobby.
Yep.
I have a quick question. It's my fault because I missed 1 second of what you just said, but I was with you to the 5 to the square root of 3 over 3. Why is there a 2 at the bottom? I apologize. I just totally missed that, where you have the 2 times the 3.
Oh, because here, if I take that 2 out and I put it here, remember that this is the antiderivative right here of secant cubed.
Oh, okay.
Okay, so that 2 then just went to there, okay? Okay, so the tangent of theta is x radical 3 over radical 5. Okay, so this is going to be a bit of a mess. Here's theta. Okay, looks like sad face theta. And it's going to be x radical 3 divided by radical 5. So this guy is going to be 3x squared plus 5. And notice back in the original problem, it's right there. So you know at least you're definitely not on the wrong track. You know, can't necessarily say you're on the right track though. Okay, so there we go. So the integral then is going to be 5 radical 3 over 6 times the secant of theta, which is the square root of 3x squared plus 5 over radical 5 times the tangent of theta. And the tangent of theta is x radical 3 over radical 5 plus the natural log of the secant of theta, 3x squared plus 5 over the square root of 5 plus the tangent of theta, which is x radical 3 over radical 5 plus constant c. And then if you want to clean it up, maybe you can clean it up. Maybe not. I don't know. All right. So for those of you that have had experience with me before, is this the kind of problem I'm going to put on the test?
No.
Not a chance in hell. I mean, look at that answer. There's like 70 of you. That's going to make me throw up. You know, looking at that over. You got to remember, when I'm grading, I'm always half drunk, if not full drunk and stoned. So, I mean, I don't want to be looking at that. I want the answer to be 2. You know what I mean? So it's, you know, my motives are very self-serving, but they do end up helping you. Like if you got an answer like that on the test, you go, oh shit, I did something wrong here. That's not, that ain't a Bobby looking thing. Okay. So this one, a little more challenging, you know, when the numbers aren't as easy. Okay. But I've given you like what I do. Okay. I factor the thing in front of the x squared out. Some people, they want to have the 1 right there. And so they might factor the 5 out. So there's more than one way to do these. I've just settled into my way of doing it.
So is
Go
it
home.
like
What's
you
up?
said, is it easier to factor out what's in front of the x all the time?
I can't say that. All I can say it's what I'm comfortable doing.
Oh, okay.
You know, it's my go-to.
Okay.
Like I told you, like Plackmeyer, you know,
Yeah.
my high school calculus teacher, x over the square root of 1 plus x squared. You know, he would put a 2 and a 1/2 in all the time, you know.
Oh, okay. I see how.
That was his thing, you know. The other thing he never did, he never changed his bounds after the U substitution. He left them as check marks, you know.
So you just left the blank. You wouldn't put 1 over 0 like you said before not to do?
Yeah, so like here's typical Plackmeyer, okay?
Okay.
So he's standing there. He looks like a, you know, he's kind of tall. He's got a mustache and like a pretty good mustache, you know. Kind of looks like a cop, like who's not on the beat though, you know, like behind the desk or something like that. So what Bill Plackmeyer would have done is he would have said, okay, let's say I'm going to go from 1. No, let's say I'm going to go from 0 to the square root of 8.
Yeah.
Why the hell not, right? Okay, so u is going to equal 1 plus x squared. Du is going to be 2x dx. So then Plackmeyer would do this, okay? Now, I don't know if he picked that up as a kid or maybe it was something that he did one day and it helped the student and he thought, ooh, I should do this all the time. I'd have to go ask him. He lives in Fallbrook. I hate that place. 1/2. Okay, now what Plackmeyer would do is he would kind of put check marks here, you know, and then he would say it's du over the square root of u. So that's going to be 1/2. Then it's going to be u to the negative u to the 1/2 divided by 1/2. It's constant c. So it's going to be the square root of 1 plus x squared. There's no plus c, it's a definite interval. Okay, evaluated at check mark and check mark. Okay. And now he plugs back in the original bounds, 0 to the square root of 8. And I think you can see why I use the square root of 8. Because it's squared 1, 9, 3, blah, blah, blah. All right. Now you guys might have, some other ones. Now before we kind of wrap it up here and stop doing, problems. Number 31 and number 32 in my book, like in number 31, what he's doing is he says, okay, if we did our trig substitution on this particular problem, what we would get is the natural log of x plus the square root of x squared plus a squared plus a constant c. And you don't have to have the absolute values here. This is not a new mistake discovered in Stewart, because x squared plus a squared is always going to be larger than x. And it's always going to be the positive, okay, in magnitude. So even if this guy is negative, this x is negative, this will turn the whole thing back to positive, okay?
Okay.
So anyways, and what you do with this is you let x equal a times the tangent of theta and just kind of go from there, okay? But what he wanted you to remember was that identity was the hyperbolic sine inverse of this x over a thing. Okay? You do this problem and this is what you would get. You look it up in the back of the book and you see this. Your first thought is, oh shit, I did the wrong problem. Well, you got to go back to chapter 3. At the end of chapter 3 in the hyperbolics, he has these identities, okay? Number 32 is another one. After that,
for this problem, he used the natural log to get rid of the square, to move everything to the left, and just put x to complete the cube, right?
no, what he did, in order to do this integral, okay, so you let x equal a times the tangent of theta.
Okay.
So dx is going to be a secant squared of theta. You plug it in, a secant squared theta d theta divided by the square root of a squared times tan squared of theta plus 1, which leaves you with just the integral of secant of theta d theta, which once again is the natural log of secant of theta plus the tangent of theta. Okay. Now the tangent of theta was x over a.
Oh, okay.
So here's theta, x over a, complete the picture, x squared plus a squared. The secant of theta is the square root of x squared plus a squared over a plus the tangent of theta, which is x over a. Okay. And looks like I have an extra a. Okay, so where did I go wrong, or did I go wrong? The tangent of theta is x over a. Okay. I think he's wrong. I think he made a mistake in the book.
Oh, okay.
Ooh, did I just discover another one?
Nice.
I'm pretty sure that has to be, let's see, maybe it would be maybe the log of a's cancel. Now it'd be minus log of a minus log of a. I'm thinking about, let's see. It's the natural log of x squared plus a squared plus x over a. All right, after we hang up here, I'm going to do this one very carefully. I think I just discovered. So now this is the third one that I know of, and the other two. I always feel good when you find. You always feel good when you find a mistake in Stewart, because look at all the acknowledgments that he makes. You know, so many people acknowledged in that. All right, flip the screen over. Laptop's about to die. Can't use it in writing mode with it plugged in. This thing sucks a lot of power. Where's the power plug? I didn't even start drinking it. Unplugged. All righty. Oh, boom. Stop broadcasting. Go back to here. Back in there. There was everybody. 50 people hung out. Okay, so there we have it. Now, I don't really think I need to tell you what to do in order to get better, do I?
You're saying don't do any integrals. Just do
don't do any.
I got you, man. I'm there.
Take a nap.
Yeah, take a nap. I got you, man. I'll go for my run tonight. Just
Yeah,
No.
these are puzzles. I remember when I retook all this in college just because I figured get an easy A. And then I didn't turn any homework, so I got an easy B. But the guy that was doing this stuff, he was that guy that had the southern drawl, walks like a duck, talk like a duck. Okay. And you know, he was always saying these are just like big old puzzles that you're, you know, working on. So if you run out of problems to do, please go to OpenStax and just do more, you know, because what we're going to be talking about tomorrow night is really not calculus at all. It's more of an algebra thing.
Oh, good.
Right. It's a partial fraction decomposition. I have to somehow explain, especially to Eduardo. And do I have any other math majors in here?
I mean, I think like all of us in CS have to only miss 2 math courses or some craziness like that. So unintentionally, we all have to do Calc 3, I think, and Boolean algebra and linear algebra and like a bunch of classes. So it's not our intent, but.
And discrete math.
Yeah, I think we can do the discrete.
That's where all the Boolean.
Yes. Yeah, I think we can do that in CS hopefully, but we're on a math track outside of not being math majors.
So let me look in the chat and see. Anybody?
I'm done with all my algebra.
What's up?
I'm done with all my algebra.
You did the Boolean and the linear and all the stuff?
Yeah, I did those a while back.
Oh, okay. Yeah.
All right, so who's the math major?
Summer too, which sucked.
Anybody still in the room that's a math major? Just type it into the chat. Because if you're a math or a physics major, I feel like you need a proper explanation of this partial fraction stuff. No textbook gives you a good reasoning as to why this works, because it requires some fairly complicated math, something that you would see as a math major as a senior, maybe at Berkeley, and in grad school anywhere else.
I recommend a lot of YouTube.
It has to do with something called the Chinese remainder theorem. And it was something that was applied to integers, but you've heard me say this many times, integers and polynomials, they behave exactly almost the same way. So this concept, this Chinese remainder theorem thing, which was a modular arithmetic thing, got applied to these polynomials, okay? So I can give a really good explanation of all of that up to a point. And then there starts to be some holes where I just would use notation and words and language that I might as well be talking about Russian, speaking in Russian. You know, if you take a ring and you mod out by a product of ideals, it's the direct sum of the one at a time quotient out guys. Again, so anyways, that's what we'll be doing tomorrow. A lot of algebra, okay? When you start off with the integral, you end up doing a shitload of algebra, and then the integral is just, it is what it is, you know? And sometimes you get lucky, it's an easy integral. Sometimes it sucks, and you just have to keep going. But the thing I want to tell you before we hang up here today is all of these problems are dreams later on. You know, when you're working out in industry, or even if you're, you know, I remember in physics, I got double in math and physics. And every now and then we got an integral in physics that we couldn't do. And so we had to do a bunch of approximation stuff that we'll be getting into here at the end of chapter 7. So you love it when you get an integral that actually has an answer, like a closed form answer, as opposed to maybe having to use the approximation techniques in chapter 7, which honestly nobody uses. Those are so archaic. But the stuff in chapter 11, the Taylor series stuff, that's what everybody starts using. All right, do you want me to get anything at school? I'm going over there. Anybody leave anything in the MBCC building that I'm gonna raid that refrigerator. I'm gonna see if anybody left some good burritos in there.
I left all the computers. You can just bring them all to me. Just all the Apple computers in the computer lab, man. I'll take.
I left a big stack of $100 bills.
Yeah, if you see any $100 bills in the cash register in the Barnes and Noble, I was accidentally over there and left them all in there. So
yeah, I left them all in there.
Yeah. Don't want them to refund me for my parking for last semester.
The $25 is it 30? Okay, I forgive them for that. I don't get why they charge us again for the health stuff for the summer class. We also pay for the health center. Yeah, I don't understand that either. I was like, why is that in our thing if we're not on campus? I'm like, why?
I get that it's a dirt sheet, but it's
same thing with the material fee. Like, what material are we paying for other than this?
Yeah,
it's so confusing.
They're charging us for our computer and our own textbook use. Notice you guys are using computers, so we need to charge you for that. No, man, it's whatever. It's not worth fighting with them, but it's like so ridiculous. It's like, oh, you can't use this, and you guys are still charging extra. Great, thank you.
Brian, are you having any problems with the antiderivatives?
Oh man, I need to spend more time on this. I'm having a problem with integrals, but like I've been doing note taking, and hopefully I plan on like trying to do a couple of these a day. I mean, that's kind of about most time I'll have for them, but yeah, man, it's definitely a lot to take in, like, because Calc 1, like I felt like I was going good till we got out of that classroom.
Yeah, the last few question on it was like number 6 on the exam was like dying.
Probably every other problem on the exam, it looked like foreign languages to me. But I feel like by the end I gathered some of it, but there's still stuff with integrals where I just don't understand. Like, why don't we just stop there? Like, when do we decide to stop when there's like a C? But I'm still.
Okay, so here's what you all can do. Okay, not just you, Brian. So if you're having trouble, like, just take a picture of it and email it to me.
Mm-hmm.
I mean, I can easily do an integral while I'm watching another episode of Parks and Rec.
Okay.
You know, or something, whatever the hell I'm watching tonight. I like that building mega machine show and build it bigger. I like watching them build big ass skyscrapers.
You should watch Alone, the History Channel survival show. It's pretty fun.
Oh, don't do that.
It's really good. It is really good. It's really good.
So when you guys get stuck, just take a picture of it, send it in the email. This device is sitting in front of me the whole time.
Okay.
And I get on it, and I don't like my emails to get all clogged up. So, and then it's a nice little break. You know, I'm usually up till about 2 in the morning. So, you know, generally when we get to 1 o'clock, I'm probably falling down drunk, and that's when my best work happens. So,
That's awesome, man.
so send it then and I'll see what I can do.
If you
Okay.
ever watch Parks and you get to a point where they have like they go to Eagleton and they get balloon art. I know it's the weirdest thing ever, but my buddy did. He's in the background. He made the balloon art for that. Like we do balloons together. It's weird. It's part of our job. But yeah, he used to do it at Disney, and he got on like these TV gigs doing it. But it was like they're like the lowest paying. Like so, he stopped doing them. He did that one, but I always thought that one was neat. Like he makes the characters, Leslie and Ben, out of the balloons. I was like, man, he did a good job. And then he. Yeah, but it's like 75 an hour where we always charged 125 an hour. So it's like they kind of rip you off because they're like, oh, you want to be on TV and also get paid less? So he stopped doing those gigs.
I had a friend that he was an extra.
Oh, nice. Yeah,
in a shitload of movies. Like he was an extra in. You remember that movie Night at the Roxbury?
Yeah, who was he? Where was he? Yeah. Emilio.
So when they're in the, you'd see him. He would like walk by, you know. And then in this one, he walked by and looked at the camera and went like that. You're not supposed to do that, but it got past the editors. But anyway, you know, he said he made pretty good money doing that.
I think it's like okay pay. If I remember from my buddies who do it, I think the thing that like everything else, it's just super inconsistent. So, you know, you might have like weeks or a month between extra gigs, but I think it's at least $20 or $30 an hour, but it's just short-term work.
Imagine
Yeah,
that.
he had done it so much that he'd worked it in. You know what he was? He's a computer science guy. He's a programmer.
Oh, neat.
And so he would always tell me, like, you know, he'd lose his job or something, and then he would go do real estate stuff, you know, like, you know, refinance, and then he'd get a job back in the, you know, computer field, but he'd have to get certified again by all of these. There's a lot of shit that just I never do it.
Yeah,
I mean, you have to be up on the guy Eric over in tech that fixes all of our computers and stuff. I mean, the guy's just got to be constantly reading about this change, that change.
Also costs a ton of money to do those tests. Like I tried doing the Oracle certification, and I only took it once because it was $250, and it's a really hard test. Our teacher told us that we'd all be prepared, like the Java 2 professor, and I think like 50 or 60% of the class took the test, and only 2 out of the 18 of us passed it, even though like we all 100%ed those quizzes and everything.
Were you one of the 2?
Oh, I wish. No, man, I'm not. When I was like 18, I would have been that guy. I was that guy. You know, I got my first grade with a 4.0. All this stuff was cake. But coming back, man, it's really hard to care as much. I just gotta be honest, you know, like it's just really hard to be like, man, I care as much about grades because like I've got a job that pays my bills for the time being. So it's like I've got that part taken care of. I mainly just want to learn so I know how to do this stuff. So when things get in my way that impede that or are to the side of it, it's really hard for me to be like, man, I want to do that thing. It's like, no. Tell me how to do this. And I find like YouTube tutorials are okay, but a lot of them skip a lot of things where it's like, wait, how did you get this? And I don't like that lack of knowledge either. So
you need to get the videos with the guy going, and this is where you do this, you know, and you know, believe it or not, those are the best people because they emphasize on steps.
I've started taking Udemy courses at the same point, like finding the best ones are like $10 and they're just like really well curated YouTube videos. Like they all lead from one to the next. But if you don't
every section in Stewart is on YouTube. Every
really?
section. Every single section, there are several lectures. So if you want to get another lecture on trig substitution, it's there.
Yeah, it's crazy. Like there's so much of that stuff, but I like the in-classroom experience. That's why I went back to OCC. You know, that's why I'm waiting for all this stuff to end to go back, is because I like talking to you. I like talking to teachers and asking a personal question. That's what
sure.
Or going up to the whiteboard and being like, no, this is what this is, you know. And
I don't know how to do this. Like, I'm a
Yeah.
dummy. Can you tell me what I did wrong? Whereas like, if I'm on Udemy, it's like, okay, now I got to Google search for 30 minutes to figure
I
this.
think Andy is doing 280.
Yeah.
I think that would be brutal to try to do 280 in this environment, at least the way I do it. I mean, I'm already having trouble with just the screen because you know how I like to use all of the board, you know,
Yeah.
and I can refer to things. 285 last semester was rough because some of those equations, they're wraparounds, you know, and so
Yeah,
yeah,
man,
I'm looking forward to going back too, kind of.
it's a weird thing for learning. I'm just glad I'm at OCC because it's a lot easier to justify a few $100 for an online class than it is for like I said, $13,000 for a semester anywhere else, or $8,000 if you're at a state school.
Yeah, there's a lot of parents right now in my neighborhood that have like graduating senior
Yeah.
going off to the University of Georgia. That's the big thing in the Newport Beach area. You got to have your kids go to some cool SEC school or something. And so like the one kid is at Ole Miss, the other one, I don't know. But anyways, now they're questioning like, okay, I can pay that, but they're just going to be taking online.
Yeah.
There's
Probably
going to be social distancing. There's going to be another outbreak in the fall.
Yeah.
Oh, I mean, it's the same outbreak. It hasn't ended.
Yeah, they're just gonna keep this going, man. And I'm not a virologist, as everybody in here knows, but I have noticed that very few common viruses, flu, cold, have ever been killed or cured completely. So, I mean, I personally, I guess I'm probably heartless and unempathetic, but it just seems crazy to constantly do something. It also seems insane to force elderly people with COVID into retirement homes, which is what they have like a law in many states where if an elderly person has COVID, they must be admitted to a nursing home. Like they cannot turn them away.
What I
So-
just heard on the news today is that they're stopping, the retain areas where they do, they retain on the highways, and they're stopping funding for what's it called, in-vehicle testing.
Oh, in people. Oh, are you talking about like for the semi trucks?
Even the semi trucks, but I mean even what's it called, drive-through, like a drive-through testing areas.
Oh, they're stopping funding for that. Okay.
Yeah. And
My
I'm
buddy
like,
Sharif, he was saying, you know, Massimo's Pizza on 17th Street?
Yeah.
Yeah, that's my friend's family's restaurant. And
Oh, nice. Good spot.
so I was up there today getting a salad, and Sharif said, you know, the reason that there's this, the reason it's spiking is because there's more cheap tests available.
Yeah.
The test that LeBron James and the gang are going to take to go play in the bubble, that's not the test that's being delivered in the Rose Bowl parking lot, you know, with a drive-through. You're getting some cheap thing from China as opposed to a better thing.
Yeah, man, I am very skeptical of the testing that we have right now. It doesn't seem to be, from what I've gathered, it's like 60% concrete, like positive even. And like you said, I imagine there are better tests that are going to people that are more important. I've also
the test that I got when I went to Spain to go see my grandparents that are out there, because that's the number one thing that I had to go because they're old.
Yeah.
They're 100 and something or other. They were like, okay, we're gonna do two tests. The one that I did here at the airport to leave to go over there was the blood test, where they prick your finger and they test it there.
Okay.
They okay you. Then when you get there, they do the one where they stick the swab into your
Up your nose, right?
Yeah,
I heard that one's really painful from everyone.
It is. If they go in and they just nick the back of your head, it hurts.
Oh.
For me, as soon as I felt them get close, I was like, you know. But thank God the person that did it didn't shove it in like
dogs out.
You know, he just literally like pulled out the swab at the end with his glove, spun it a little bit so he could get back there and just, you know.
Eduardo, when do they tell you though whether you were positive or not? Does it take like a day? Does it take 2 days?
Actually, it doesn't take that long for the blood. The faster one is the blood.
Okay.
The one where they pick your finger. The one that takes longer is actually the one they stick in your with the swab. It takes, I think like it took them 6 hours to do.
Okay.
So we were stuck in the airport for like 6 hours while they gave me.
What would they have done if you tested positive, man? Like, cause how much would that have sucked if you went to Spain and it's like, hey, you test positive, man. Sorry.
So what happened is when they did my blood test on the thing, they tested it and I had the antibiotics.
Okay.
So they were like, so you got it at one point and you're okay. I'm like, well, I guess I'm A positive, but I mean, this was in February and
Yeah.
I still have remnants of the antibodies in my system. My wife had it, because she came with me, and she same thing, antibody positive. So thank God we didn't leave, like, and we were all like, when we went to school and stuff like that, because I was in school.
Yeah.
I am a germaphobe. When I'm sick, I'll go to school, but like I'll have my face. You saw me going to class with my scarf, and I was like this.
Oh, I remember that.
Like,
I totally remember that.
Yeah.
I used in the front, Eduardo, so I actually don't remember this, but
okay.
I believe you.
Yeah.
I
And
totally
like,
do.
and when I was coughing too much, I just literally would cough into my scarf and walk out the class. You know, I didn't want to get anybody else sick.
Yeah.
You know, I avoided at all costs sneezing into my hands. I would never sneeze into my hands, just blatantly like that. I
Ask
always
somebody
go
else
lift up
if
my
you could
shirt
use
or
their
grab
hands.
my scarf and cover myself. You know.
Yeah.
Yeah.
I am concerned that we're going to be making like something like being sick into this like leprosy level of disease that it was never before. Like, I've been really lucky that I have probably coughed 2 times in the last 3 months total. But I have wondered, because I've had to be around people a few times doing drafting or whatever, and it's like, I'm wondering if like you swallow. That happened to me actually the other day when I was around people. I swallowed spit down the wrong throat, and I was like, I just wonder like, what do people think? Like, I'm trying to hide this thing now, and it's like, I guess like the not that I'm that old, but the old man side of me wants to be like, can't people just remember that it's normal to be sick? Like, that was a thing we all used to deal with on a daily basis. But
I mean, I believe by next year's spring, this is gonna be completely gone.
I've heard the political thing where it's like by November it's going to be done. But here's the thing, man. Like, and that's the thing that makes me not think it's not super political at all is the fact that it was worldwide. And the thing that makes me think it's not going to be done by spring is that the vaccine is so trials normally take 18 months. And then I'll be honest, I'm not a big heavy I'm not a huge vaccine dude.
One of the companies that's involved in making the vaccine.
Yeah.
Years ago, my buddy Eric, who was an investment banker, he got me one of these inside tips. One of these deals about this company that they were making a synthetic flu vaccination. The people that can't do the chicken egg thing, whatever. Okay. So I bought this stock at about an average of maybe $1 a share.
Nice.
Okay. And I bought like $5,000 worth, and I sold it like when they went into phase 3 trials and everything was good. I sold it at $14 a share.
Nice.
So I made a shitload of money. Okay.
Yeah, that's great.
And then the stock tanked.
Oh, wow.
Yeah.
Okay. But
it's always after the testing phase.
Well, something happened with the 3rd phase of the test, but then the stock went back down. My buddy Eric, who never sells anything, he goes, God damn it, I should have sold it, because it went back down to like $2.
Yeah.
And he had bought a bunch at $3. Like, I just did my one-time buy.
Yeah.
Okay. Then I see on the news, this same company is involved with the coronavirus vaccine.
Okay, they're one of the companies, like one of the 8 or so.
Yeah.
Just look today. That stock today, let me tell you what the high was.
This is probably gonna be a bummer.
Oh, it is.
It's gonna be probably 50 cents.
No, it's probably gonna be crazy, man. It's probably gonna be
The high, it closed it closed today at $70.05.
Yeah, I had a feeling.
The
yeah.
high was 80. I sold at 14. So I could have made 80 times $5,000 if I
It just reminds me of my experience with, I remember sitting in class with a buddy. We were at Cal State Long Beach. He's like, you really think about Bitcoin? I'm like, man, this all feels weird. It's $40. And I was like, but maybe I should. Maybe I should just buy like $500 worth, which I did the math. I would have had like $20,000 or $30,000 if I would have bought just $500 worth of Bitcoin and sold out early, not even at the $20,000 level. But you can't, the problem is you can't just beat yourself up about stuff that nobody would have ever expected Bitcoin to get to $20,000. Nobody ever expected to get past $2,000. It's not real.
March was my wife's sister works at Seattle Tech.
Yeah.
And they were doing something with splint cells and something like that. And their stock was valued at $15.
Yeah.
Right. And they jumped all the way up right before they moved over to testing phase.
Yeah.
And the market was going to close. It jumped to $300 and some $10.
Wow.
And my wife's like, "Did you buy it?" I'm like, "Yeah."
You did?
Yeah.
Hey,
And she's like, "What made you think of selling it?" I'm like, "Right before the testing phase." I'm like, I always feel like it's better to always sell before.
Oh, you sold before it got to the $300.
Exactly. Yeah.
Oh no, man.
But it was like 200 and something, 230 something. Yeah, I still made out okay.
Yeah.
I wish I would have held out for another 100, but I was like, greed never pays off.
It's like right now, I was telling, there was a guy in Calc 1, Magnus, I was telling him, like, if the stock market crashed while we're still in class, I was like, don't buy right now. There's going to be a second crash. And look at it. It jumped up back where it was before. There will be a second crash, but, like, I don't know when, and I don't know how low it's going to go.
Well,
so
it's crashing right now. I mean, everything is crashing right now except for the majors.
but it's not crashing like where it was in
March. No, like in March now.
That was ridiculous, man.
March was stupid. Yeah. I know Disney right now is like at barely surviving. They're at 115 today.
Disney is they're not going anywhere. Even if they do go somewhere, somebody else will buy them up. It's like that's a company that's never going to disappear.
Oh no. They I'm wondering if they're gonna go back to their original thought where they're not gonna open 2020, they're gonna open 2021. If they don't open 2021, then they're gonna. I know they're what's it called? China. One of their parks is open right now.
China is Shanghai. I have a friend who's been there.
Shanghai. I've seen videos of people going to that park. It's odd. It's weird.
It's odd, but man, like it's either that or you're a company who essentially is they're still gonna make stupid money, but they're gonna lose. I think they $1 billion a day.
Yeah,
lose $1 billion a day. I think.
And then their Dreamworks program. I don't know if you know what that is.
I don't actually know.
Dreamworks program is a university for people that do art.
Okay.
An art university through Dreamworks.
Oh, nice.
Yeah.
Hey, Dreamworks was owned by Steven Spielberg. I thought that was owned by a different company.
They got bought out, I believe.
Dreamworks?
But I thought, Dreamworks is Disney. I think it's always been Disney.
No, Dreamworks is Universal, man.
Oh, no, okay. Which one's the other one?
They own Pixar.
Oh, yeah, Pixar. My bad.
No worries, man.
I'm confused.
No problem.
Pixar's Disney, isn't it?
Yeah.
Disney, Dreamworks is Universal. Dreamworks, I think, was owned by Steven Spielberg at one point, if I remember correctly. Yeah. Anyways, dude, I would love to chat about this. I gotta get going before I lose. I've already lost all the sun, but I want to go for a run real quick.
I'm going over to campus.
All right.
You guys email me your questions and while I'm watching TV, I'll just work it out and send it back to you. Okay.
Okay, Professor. Thank you.
All right, guys.